Every generation of long-haul jet has been sold on the same promise: more range, farther nonstop routes, more oceans crossed without a fuel stop, bigger numbers on the spec sheet at the air show. So when Boeing rolled out the 787-10, the largest member of the Dreamliner family, industry watchers expected the usual story: a stretched fuselage, more seats, and presumably even more range than the jet it was built alongside. Instead, Boeing did something that looked, on paper, like a step backward. The 787-10 flies roughly 1,200 nautical miles less than its sibling, the 787-9, and airlines bought it anyway, in large numbers, at list prices north of $300 million each before discounts. Delta ordered 30. British Airways confirmed 32. United didn't just order new ones, it went back and converted dozens of existing 787-9 orders into 787-10s instead. Etihad, Air Canada, Singapore Airlines, all in. So what's actually going on here? Why would airlines pay a premium for a jet that flies noticeably shorter than the one right next to it on Boeing's own order sheet? The answer isn't a mistake, and it isn't a compromise either. It's one of the more interesting strategic bets in modern commercial aviation, and understanding it tells you something important about how the entire long-haul industry actually makes money, as opposed to how it looks from the outside. Let's start with the numbers, because they matter and because they're genuinely surprising if you've never looked closely at the Dreamliner family before. The 787-9, the mid-sized member of the family, is generally quoted with a maximum range around 7,065 nautical miles, the longest published figure in the entire 787 lineup. The 787-10, the largest and newest variant, comes in at roughly 6,330 nautical miles in its baseline configuration, a gap of well over 200 nautical miles between two aircraft that share the same wingspan, the same cabin cross-section, the same engines, and the same fundamental Dreamliner DNA. Boeing has since certified an increased maximum takeoff weight upgrade for both jets that claws back some of that gap, adding roughly 400 nautical miles of extra range to the 787-10 when airlines opt for it. But even with that improvement factored in, the 787-10 still trails the 787-9 by a meaningful margin. To put the original gap in real-world terms, a 787-9 can comfortably fly nonstop routes like Los Angeles to Singapore or London to Perth. Hand that same mission to a standard 787-10, and it simply can't make it without a fuel stop or a serious payload restriction. That's not a rounding error in an engineering spec. That's an entire category of route quietly removed from the aircraft's capability on purpose by the same manufacturer, using the same underlying technology that produced a longer-range sibling sitting right next to it on the factory floor in Everett, Washington. Here's what makes that decision so strange if you think about it from the outside. Long-haul aviation has spent the better part of a century treating range as the ultimate scoreboard. It's the number airlines put in the headline of every fleet announcement. It's the number that decides whether a route between two cities is even physically possible without a stopover. Airbus built the A350-900 ULR specifically to chase the title of longest non-stop commercial flight in the world. Dassault markets its business jets on how many time zones they can cross in a single hop. In that culture, deliberately building a shorter range aircraft looks, at first glance, like handing your competitor a marketing advantage for free. And yet Boeing did exactly that, on purpose, with full knowledge of what they were giving up before a single rivet went into the first 787-10 airframe. That's not the profile of an engineering mistake. That's the profile of a calculated trade-off. And trade-offs like that only make sense once you understand what airlines actually optimize for, which is very different from what most passengers assume they're optimizing for. Because here's the thing, almost nobody outside the industry fully appreciates. Airlines don't primarily think in terms of how far a jet can fly. They think in terms of cost per available seat mile, essentially how much it costs to move one seat 1 mile, averaged across an entire flight. That single metric, more than any range figure on a spec sheet, determines whether a route makes money, how frequently an airline can fly it, and ultimately whether the aircraft pays for itself over its operating life. Range matters enormously on the small number of routes that genuinely need it, the true ultra-long-haul missions like Singapore to New York or Perth to London. But those routes are a small, specialized slice of the overall long-haul market. The vast majority of long-haul flying happens on what the industry sometimes calls thick, dense corridors. London to Dubai, Tokyo to Singapore, New York to London, Chicago to major European hubs, all routes flown multiple times daily, packed with business travelers, connecting passengers and cargo, running well within 6,000 nautical miles one way. None of those routes need anywhere close to the 787-9's maximum range. What they need is capacity, reliability, and a cost structure that stays efficient at high frequency, day after day, year after year. That's exactly the gap the 787-10 was built to fill, and once you see it through that lens, the range trade-off stops looking like a weakness and starts looking almost obvious. The 787-10 carries roughly 40 more passengers than the 787-9 in a typical layout, using the same engines, the same fuel-efficient composite structure, and the same cabin pressurization and humidity improvements that made the original Dreamliner such a leap forward for passenger comfort. Spread the same fixed operating costs, fuel burn, crew, maintenance, airport fees, across more seats per flight, and the cost per seat drops, even if the total fuel burn per flight goes up slightly. More seats filled at similar or better margins, on routes that were never going to need the extra range in the first place, translates directly into a better performing aircraft on the routes that actually matter to an airline's bottom line. The 787-10 wasn't designed to fly further. It was designed to make every single flight it operates more profitable on the routes airlines were already flying constantly. Range was the number everyone in the press fixated on. Profitability per rotation was the problem Boeing was actually solving. United Airlines' recent fleet decisions make this strategy almost impossible to miss if you're paying attention to how real airlines allocate their aircraft orders. United didn't just place a fresh 787-10 order, it went back and converted a substantial chunk of its existing 787-9 orders into 787-10s instead, explicitly citing capacity growth and per-seat efficiency as the reasoning. United still relies heavily on the 787-9 for its genuine ultra-long-haul missions, the kind of routes where range really is the deciding factor. But for the rest of its European, South American, and North Asian network, routes with strong demand density but comparatively modest range requirements, the airline has concluded that the extra seats on a 787-10 beat the extra range on a 787-9 almost every time, because those routes were never going to use that. Extra range, anyway. Delta reached a similar conclusion when it placed its own order for 787-210s aimed specifically at dense transatlantic and South American routes, rather than ultra-long-haul missions. British Airways is bringing 787-10s into its Heathrow long-haul network for largely the same reason. This isn't one airline making an unusual bet. It's a pattern showing up across multiple major carriers on different continents, all independently arriving at the same conclusion about where the real value in this aircraft actually sits. Turning that strategic insight into a real, certifiable, safely operable aircraft, though, was a genuinely difficult engineering problem. And this is the part of the 787-10 story that rarely gets the attention it deserves. Stretching a fuselage sounds simple in theory. Cut the tube, add a plug, weld in extra rows, done. In aerospace engineering, that kind of simplicity is dangerous, because nothing on an airliner exists in isolation. Every structural change ripples outward into dozens of other systems that all have to be rebalanced together. A longer fuselage means significantly more bending moment concentrated right at the wing root, the exact junction where the wing meets the body. And that stress gets applied over and over again across tens of thousands of flight cycles spanning decades of service life, through every takeoff, every landing, every pocket of turbulence at cruising altitude. Boeing's engineers weren't starting from a blank sheet of paper here. They were taking an airframe that had already been optimized close to its practical limits on the 787-9 and asking it to safely carry meaningfully more weight and more passengers without simply piling on extra structural mass everywhere, which would have destroyed the fuel efficiency that made the whole Dreamliner program worthwhile in the first place. The actual solution involved targeted reinforcement, adding structural material precisely where stress concentrated most, at the wing box, at key fuselage joints, while leaving the rest of the airframe as close to the 787-9's proven lightweight design as possible. That balance, enough strength to be certified safe across the aircraft's full operational life, without enough extra weight to erode the efficiency gains that justified building a Dreamliner in the first place, is where the genuinely hard engineering work happened, mostly invisible to anyone just looking at the finished aircraft from the tarmac. The system's challenge ran in parallel and was arguably just as demanding. More passengers on board means more of everything: more air conditioning load to keep a fuller cabin comfortable, more electrical demand for lighting, entertainment, and galley equipment, more hydraulic capacity for control surfaces and landing gear cycling more often on shorter, more frequent flights, more heat that has to be managed and dissipated across an airframe that was never given a fundamentally new power architecture to work with. Boeing's engineers had to redistribute and optimize the load across essentially the same underlying systems architecture that powered the 787-9, squeezing meaningfully more output from existing components without pushing any single one of them past its certified operating limits. It's a bit like adding several extra floors onto an existing building without being able to touch or expand the foundation underneath it. Every additional load has to be absorbed by systems that were sized for a smaller aircraft. And there's very little room for error because in aviation, a miscalculation in a system like that doesn't show up as a gradual warning sign. It shows up as an outright failure, and failures in flight critical systems aren't acceptable at any stage of certification. Then there was the manufacturing challenge, which gets even less attention than the engineering, but which genuinely tested the entire Dreamliner production system. The 787 is built in large composite sections across multiple facilities scattered around the world, then shipped and assembled at Boeing's final assembly line in Everett, Washington, an elegant distributed manufacturing model that worked well for the 787-8 and 787-9. Stretching the fuselage for the 787-10 pushed the physical size of those sections closer to the practical limits of what could be transported and precisely aligned during final assembly. Tolerances that had been perfectly workable on the shorter variants became genuinely tight constraints at this larger scale, and Boeing had to redesign portions of its assembly sequencing and adapt specialized tooling to accommodate the larger sections reliably at production rate without introducing new sources of manufacturing risk or quality variance. In a very real sense, building the 787-10 wasn't just about designing a longer airplane. It was a stress test of the entire Dreamliner production ecosystem Boeing had built up over the preceding decade. And getting that stress test right mattered just as much to the program's eventual success as getting the aerodynamics or the structural engineering right. Step back and look at where this has actually led the industry. Because the shift the 787-10 represents isn't just a footnote in Boeing's own product family, it's part of a broader pattern reshaping how long-haul aviation gets planned across the board. For most of the jet age, range was the number that defined ambition. It was on every press release, every airshow banner, every glossy spec sheet, handed to journalists. An airline's fleet strategy was, in large part, judged by how far its longest-range aircraft could fly nonstop. That scorecard hasn't disappeared entirely. Ultra-long-haul flying is still very much a real and growing niche. The Airbus A350-900 ULR still flies genuine marathon routes like Singapore to New York, and there will always be a market for pushing the outer limits of nonstop range. But the center of gravity in long-haul aviation, where most of the actual flights happen, where most of the industry's revenue is generated, where airlines build durable, sustainable long-term businesses rather than headline-grabbing route announcements, has quietly shifted toward dense corridors, high frequency, and unit economics rather than prestige range figures. The 787 Kakata 10 didn't just happen to arrive alongside that shift. In a real sense, it helped drive it by giving airlines a credible, efficient way to lean into that strategy with an aircraft purpose-built for exactly that mission profile, rather than a compromise aircraft trying to be everything to everyone. Look at how carriers around the world are actually deploying the 787-10 today, and the pattern becomes hard to miss. Singapore Airlines, the launch customer for the type, uses it on high-frequency regional and long-haul routes across Southeast Asia and into Europe, not because those specific routes demand extreme range, but because they demand capacity that stays profitable at scale, flight after flight, day after day. Etihad operates the 787-10 on long-haul connections out of Abu Dhabi into Asia and Europe, corridors dense enough with demand that filling extra seats matters more than squeezing out extra nautical miles. Nobody on that particular route actually needs air. Canada, United, Delta, and British Airways are all following essentially the same logic across different networks and different continents, each independently concluding that on the routes where they actually fly the bulk of their long-haul capacity, a shorter range, higher capacity jet beats a longer range, lower capacity one on the metric that actually decides whether a route makes money over its operating life. None of this means range has become irrelevant as a design consideration, and it's worth being precise about that. Because overcorrecting into range doesn't matter anymore would be just as misleading as the original assumption that more range is always automatically better. Ultra-long-haul routes are real. They're growing in number as airlines chase new nonstop city pairs that were previously impossible, and aircraft purpose built for that mission, like the 787-9 and the A350-900 ULR, remain genuinely essential tools for the specific airlines and specific routes that actually need them. What's changed isn't that range stopped mattering. What's changed is that range stopped being treated as an automatic, unconditional virtue that every long-haul jet should maximize by default, regardless of what routes it's actually going to fly for the next 20 or 30 years of its operational life. Boeing looked at where the real, sustainable long-haul revenue in the industry actually sits, mostly on dense, high-frequency corridors well within 6,000 nautical miles, and built a variant deliberately optimized for exactly that reality, rather than for winning a headline spec sheet comparison against Airbus. It's worth pausing on why this particular trade-off, seats versus range, tends to favor seats so heavily on dense corridors because the math behind it isn't obvious unless you actually walk through it. Imagine two versions of the same route flown daily. One on a jet with 40 fewer seats but hundreds of extra nautical miles of unused range, and one on a jet with 40 more seats, but exactly enough. Range to comfortably cover the mission with reasonable reserves. The fuel cost difference between those two aircraft on that specific route is relatively small because neither one is actually using the extra range in practice. The fuel burn scales mostly with the distance actually flown and the weight actually carried, not with the aircraft's theoretical maximum capability. But the revenue difference is not small at all. 40 extra seats, filled at a reasonable load factor, multiplied across 2 or 3 flights a day, multiplied across a full year of operation, adds up to a meaningfully larger revenue base sitting on top of a cost structure that barely changed. That's the entire logic in a nutshell. Unused range is a capability an airline pays for anyway, in the form of the increased structural weight and fuel capacity built into a longer range airframe, whether or not that route ever calls on it. On a route that will never need that range, all of that engineering is dead weight, quietly hurting fuel efficiency and payload capacity without ever earning its keep. Reclaim that unused capability as passenger seats instead, on the specific routes that don't need it, and you turn wasted engineering margin directly into extra revenue. This is also why airline fleet planners increasingly think in terms of mission-specific aircraft, rather than a single do-everything jet, and the Dreamliner family as a whole is really a case study in that broader philosophy. Rather than building one 787 variant and forcing every airline to accept a single compromise between range and capacity, regardless of their actual network, Boeing built a family. The 787-8 for thinner long-haul routes that don't justify a larger aircraft, the 787-9 as the versatile middle ground with the family's best range for genuine ultra-long-haul missions, and the 787-10 purpose-built for dense, high-frequency corridors where capacity beats range every time. Airlines then assemble their fleets like a toolkit, matching the right variant to the right mission, rather than trying to force one airframe to handle every route in the network equally well. That's a meaningfully different design philosophy from the way long-haul aviation used to work, when airlines often had to accept whatever single long-range configuration a manufacturer offered and simply fly it everywhere, whether or not that particular mission actually needed all that capability. It also explains why the order numbers for the 787-10 look the way they do relative to its siblings. Across the Dreamliner program as a whole, the 787-9 remains by far the best-selling variant, accounting for the large majority of total Dreamliner orders, precisely because its balance of strong range and solid capacity makes it flexible enough to serve as an airline's default long-haul workhorse across almost any mission. The 787-10, by comparison, occupies a smaller, more specialized slice of the order book, but a fast-growing one because it isn't trying to be everyone's default choice. It's trying to be the clear, obvious answer for a specific, defined problem. Dense, dependable dense corridors where an airline already knows it needs more seats more than it needs more range. Judged against the 787-9's broad, flexible role, the 787-10 will probably always look like the smaller player in the family by total order count. Judged against the specific mission it was actually designed for, it's arguably the most precisely targeted aircraft in the entire Dreamliner lineup, which is exactly the kind of specialization that tends to age well as airline networks mature and route planning gets more sophisticated over time. So the next time you see a Dreamliner at the gate and notice it's the longer, larger 787-10 variant rather than the 787-9, understand what you're actually looking at. It isn't a shorter, lesser version of a better aircraft sitting somewhere else on Boeing's order sheet. It's a purpose-built answer to a question most of the industry wasn't asking loudly enough at the time. On the routes that actually generate the bulk of long-haul airline revenue, day in and day out, does an aircraft need more range, or does it need more seats filled at a lower cost per passenger? Boeing's engineers answered that question with a very specific number. A jet that flies roughly 200 nautical miles shorter than its own sibling, and airlines around the world have spent the years since backing that answer with real orders, real fleet conversions, and real route deployments. The range is shorter. The economics on the routes this aircraft was actually built to fly clearly aren't, and that quiet strategic bet is a big part of why the 787-10 keeps landing on order sheets, even though, on paper, it looks like a step backward from the jet sitting right next to it in Boeing's own lineup. There's a broader lesson here that extends well past the 787 program itself, and it's worth sitting with for a moment. The most consequential decisions in commercial aviation rarely announce themselves with a dramatic headline number. They show up quietly, buried inside a spec sheet most passengers will never read closely, inside a fleet order that gets a brief mention in a traded publication. and then disappears from the news cycle within a week. Nobody outside the industry was talking about cost per available seat mile when the 787-10 launched. Everyone was talking about the range gap, because range is the number that's easy to understand at a glance. Easy to put in a headline, easy to compare across competing manufacturers. But the number that actually determined whether the 787-10 succeeded or failed as a business proposition was never the range figure at all. It was whether airlines could fill those extra 40 seats, route after route, year after year, at a cost structure that beat the alternative. That's a much less dramatic story to tell, but it's the story that actually decides which aircraft end up profitable for the airlines that fly them and which ones end up parked early. And it's a pattern worth watching for the next time a manufacturer rolls out a variant that looks, at first glance, like a step down from its own sibling.